Okay, hello. I'm going to talk about some work I've done recently with a number of colleagues here. Here are the references. There are two papers here in Physical Review D and one paper coming. What we describe in these papers is something that I've been calling a hadron structure oriented, or HSO, approach to doing phenomenology with transverse momentum dependent, or TMD, parton densities. So my goal here is to explain in as clear and concise a way as possible what we're doing here, what we mean by hadron structure oriented, and so forth. So to establish context, we're thinking about processes like semi-inclusive deep inelastic scattering, transversely differential in the transverse momentum. So there's some proton and an electron coming in with an exchange of a virtual photon. And it's a highly virtual photon, so probing very short distances. And the idea in semi-inclusive DIS is that you look at and count the number of hadrons of a certain type coming out. So the one labeled PB here. And the idea is if the transverse momentum, or if this hadron is basically coming out back to back, aligned with the proton, and you can resolve the transverse momentum, this small transverse momentum, then you can maybe get information about the non-perturbative things that are happening inside the proton and inside the hadronization procedure for this process, and relate it to the more fundamental questions about how non-perturbative transverse momentum is generated. So the picture starts with this kind of transverse momentum dependent factorization that many people watching may have seen before, where you've got a parton density that's sensitive to both a longitudinal momentum fraction and a parton's transverse momentum, so K1T here. And it interacts with the photon and scatters with some probability. And then you multiply that probability times the probability that the outgoing parton turns into a hadron of a specific type, of a type H labeled here. And this is a nice picture that we have in our minds. This is the formula that you see. And here's the picture, of course. Many people are more familiar with this formula when it's written in coordinate space. So if we take each of these transverse momentum dependent correlation functions, a transverse momentum dependent PDF and a transverse momentum dependent fragmentation function, we take each of those and Fourier transform into a transverse coordinate space, then the convolution over a common transverse momentum simply becomes just a product of a transverse coordinate dependent parton density and a transverse coordinate dependent fragmentation function, and then take the transform of that to get back into the QT space. That's a basic setup, again, to kind of provide context. That's kind of process you might see at Jefferson Lab, and hopefully in the future, an electron ion collider, or an EIC. So what am I getting at when I talk about hadron structure approach, a hadron structure approach? Well, it starts from the idea that many of us think about these collisions in terms of a parton model picture, sort of like what I just described when discussing this semi-inclusive DIS process. And it's a very nice simplistic picture that you can almost think of in terms of billiard balls and so forth. If we're talking about the most familiar situation, say totally inclusive deep inelastic scattering, then a cross-section might look something like this. So you have a cross-section differential in hardness and in Bjorken X, and up to some factors, it will be proportional to some parton density. So basically, it's going to be directly related to the probability that you find a parton in the colliding target with a particular momentum fraction X, which in this parton model picture, we can relate very directly to the longitudinal momentum fraction. So this is the usual X equals Q squared over 2 P dot Q. But when we go to QCD, the picture changes a little bit. I mean, we sort of preserve the basic overall structure, but with some important caveats. For one thing, the parton density in QCD, well, we know how to write down a precise definition for that. So we have a precise definition. And like many things in renormalizable quantum field theories, it has to be renormalized, and it acquires dependence on a scale. So this object isn't like 100% universal now. It depends on the scale at which we're probing it, but we know via evolution and all these things how to deal with that. And then it gets convoluted with or multiplied in a very general sense with some hard part that's sensitive to the details of the specific process. So in this case, deep inelastic scattering. And if we arrange things just right, it's something that we can calculate order by order in a coupling constant, running coupling constant evaluated at the scale of the process. So if the process is very hard, coupling is small, and we can essentially justify the picture above by saying it's simply the zeroth order contribution to this full factorized QCD quantum field theory expression. And we have a similar path that we follow when we're talking about the semi-inclusive case. So in that case, the simplistic parton model would simply be a probability density for finding quarks or partons of any type with some momentum fraction and transverse momentum times the probability to hadronize into a particular hadron, H. That would be pretty much all there is to it. I mean, there'd be this integral over some common transverse momenta, relating them to physically observable transverse momentum, but that would be pretty much all there is to it in a parton model picture. Now, just as before, we have to transition into something that takes into account the full QCD. And by the way, this is the picture that we have for small transverse momentum. So when the QT is very small and we're looking at the hadron coming out in such a way that we interpret what's going on as being due to the intrinsic or non-perturbative transverse momentum in the target or in the hadronization procedure. If transverse momentum is large, that starts to become essentially a perturbative tail effect. And so in the parton model picture, the very crude picture, we might be tempted to just say that that doesn't contribute or is negligible. But when we go to QCD, we have all sorts of effects we have to account for. We have to do the full factorization. So just like in the case of the inclusive DIS back here, we have definitions, precise definitions that are now accepted and more or less understood for the transverse momentum dependent parton densities and for the transverse momentum dependent fragmentation functions. They have operators that come with them and so forth. And again, they require renormalization. It's a little bit more complicated, a little bit a kind of a special type of renormalization that involves two parameters, two running parameters. But in the end, the end result is that these objects, again, acquire some sensitivity to the external scale, the external probing scale, which I'm calling Q squared here. And there's an overall hard part, just like this hard part in inclusive DIS. There are other complications. For one thing, we actually want to eventually take into account that at large transverse momentum, we can describe the scattering. I mean, things don't go to zero there. In principle, we should be able to describe the transverse momentum of order the hard scale using collinear factorization. So that's when, so that's essentially when we lose that sensitivity to the intrinsic non-perturbative part of the transverse momentum, and everything is just a tail radiated away from collinear PDFs. Okay, sometimes people call that the Y term, and then the main part, the part that involves TMD PDFs and fragmentation functions, sometimes they'll call that a W term, but okay. Okay, so again, this is all just set up. When I talk about this stuff, I do get a lot of questions about just what exactly is my point, why I'm doing what I'm doing. And so I'm intentionally building up slowly here to explain what do I mean by hadron structure oriented. And some of it comes from motivation. So you can think about things that you find said about transverse momentum dependent factorization in various places. And this is an example from the EIC's website, which I link here. You see things like, well, we want to look at three-dimensional snapshots of hadrons. So part of that's generalized parton densities, but we also say that we want to see how particles are distributed and moving inside the hadrons, and give this nice interpretation to what we're seeing in various types of data. And the point is really to take that goal seriously and figure out how to organize the theory so that we can interpret things in this way. That's essentially the larger, broader goal to all of this. To motivate it even more, go through a few scientific examples. One thing I want to point out is that when we talk about cross-sections, differential cross-sections in phenomenology, and try to relate them to things like hadron structure, we really tend to divide up the regions of the data into regions of transverse momentum and assign interpretations by region of transverse momentum. So here's a prime example here. This is a compass data taken from here, and relatively low q squared, and you have a distribution of transverse momentum. And the idea is that if we try to see the pattern of the data as we go from small transverse momentum to large transverse momentum, if we try to interpret that, maybe we can identify different shapes with different types of underlying physics. And that's what's going on here, as you can see directly from quote that I provide from the paper. So the idea is that if you fit two different Gaussian shapes to these data, you can sort of identify one Gaussian with a very small transverse momentum and another Gaussian with a larger transverse momentum. And then it's very tempting, maybe correct, to say that this small transverse momentum line is somehow more associated with intrinsic or non-perturbative transverse momentum, while as you transition to this large transverse momentum region, you've got some kind of tail, perturbative or maybe semi-perturbative tail. And we can discuss that. The point I'm trying to make here is that when we talk about data in this way, these kind of data, it's important that we be able to go region by region in transverse momentum and discuss what's going on. Some other theoretical examples that are related to this first example that I showed. There's a drive to try to understand the different types of both perturbative and multiple non-perturbative mechanisms that might be going on under the hood that explain these different shapes. So for example, what is the non-perturbative distribution of C quarks, for example, versus valence quarks? So you see some studies that attempt to model that and also extract that from data. And then there are specific physical mechanisms for describing the different types of non-perturbative behavior. So for example, in the work by Schweitzer and collaborators here, there's an identification of different types of non-perturbative regions, like there's a chiral symmetry breaking region, and then it's kind of separate from the physics of the confinement. And all of this I'm bringing up just to motivate the approach that I'm wanting to advocate here. Even if you go to very high energies, you'd like to be able to relate all these non-perturbative type structures, these non-perturbative type of studies across a wide range of scales. So you shouldn't have any contradictions, at least when you go to a different scale and study transverse momentum dependent PDFs. So even in high energy physics, like in the study of the spectrum of W and Z bosons, the non-perturbative part is important. And I just provide one reference here to make that point. This is at like almost an order of magnitude different scale. But you see that the peak in the distribution for the W is, for the Z that is is sensitive to this non-perturbative input. So all of these different scales are related, and be good to get a handle on that. So, okay, so the interpretational issue is important enough that it's worth belaboring it a little bit more. This TMD type of description fits into a larger kind of picture that people have of all different types of non-perturbative correlation functions that can be related in different ways. So for example, you'll find, here's a reference that I found, showing generalized transverse momentum dependent parton densities, and then they get related to GPDs. You know, when you integrate over transverse momentum, you get the generalized TMDs related to TMDs, the objects I'm talking about. And all of these objects are related to each other in different ways. And then if you interpret these objects, these distribution functions, as being literal distribution functions, like in the sense of probabilities, probability densities, then these relations are very kind of obvious or intuitive. For example, if I have the distribution of partons in transverse momentum and longitudinal momentum, and I integrate over all transverse momentum, I should get back the distribution, the standard collinear distributions, which are probability densities in the naive interpretation, in terms of collinear momentum fractions. Okay, so take integrals over transverse momentum, and I just get something averaged over transverse momentum. So if I integrate over transverse momentum, in the naive interpretation, I should just get back the density in longitudinal momentum, and that's that. But in real QCD, these transverse momentum integrals tend to be divergent, and that causes all sorts of technical troubles, but it also challenges this simple interpretation that we like to have. We have to figure out how to deal with that. So one of the things about a hadron structure approach, like the type that I'm advocating, is that you'd be able to preserve these interpretations as much as you can. So I'll be talking about that in just a bit as well. This is related to work that's currently ongoing. Okay, this is not just all philosophical stuff either. I mean, there's a tendency to wonder, what am I doing here that's different from what is normally done, what is done in the standard way that these things tend to get done. And I also want to make the point that there are concrete practical reasons for worrying about these things. I'll give some examples at the end. But just to get started with, here's an example of, an extraction of TMD PDFs in Drell-Yan scattering from the, say, the JAM collaboration, which makes an interpretation of Drell-Yan data that is that the width of pion TMD PDFs, the width in coordinate space, is narrower than for protons. Okay, and it's important that the assertion here is that what's being talked about is the non-perturbative part. So the stuff that you'd like to identify with the structure, the interior of the particles. Okay, so here's a quote from that paper, and I've put it in question marks because after I talk about the hadron structure approach that I'm advocating, we want to come back to this and question this interpretation. And now, another question that I frequently get asked before I even start talking about the hadron structure approach is why I'm worried about these large transverse momentum type effects, like what happens when you integrate over transverse momentum, overall transverse momentum, especially when the topic is about semi-inclusive DIS, where often the scale Q is not so large, and the range of accessible transverse momentum is comparatively restricted. Why am I worried so much about that tail stuff? And there are some very good reasons to worry about it. So for one, well, I've drawn a sketch here, an intuitive sketch of what you might imagine in your head, the shape of a transverse momentum dependent PDF in transverse momentum space, what that might look like. You've got some bump down here, and then a tail way out here. The bump you would want to, you'd be inclined to associate with some sort of non-perturbative intrinsic transverse momentum. And you might say, well, what if this shaded region here is really all I can hope to be directly sensitive to in some moderately low scale semi-inclusive DIS measurement? Why do I care about what's happening out here? Well, the answer is that at the theoretical level, we know exactly what the transverse momentum dependent PDF is for all transverse momentum from 0 to infinity. It's got a completely unambiguous or almost completely unambiguous operator definition. If we knew how to calculate everything in QCD, we could get exactly what it is. And what happens out here at the large transverse momentum has to be consistent with what happens at the small transverse momentum. There are consistency relations between what happens at small transverse momentum and large transverse momentum. So knowing what is happening out here puts some constraints on what happens down here at small transverse momentum. And we need to, I mean, if we want to interpret data in a meaningful way, we need those things to be, we need those constraints to be there so everything is internally consistent at least. The other reason is that eventually we probably want to take these PDFs and compare them with what we get in other venues and other experiments. So higher scales, for example, Drell-Yan or something like that. Then we have to go to larger Q. And as you go to larger Q, you get access to larger and larger regions of transverse momentum. And you don't want something that you've extracted from measurements at lower Q to turn out to be totally inconsistent to something somewhere else. And so having that treatment of the transverse momentum over the whole range of transverse momentum built in from the beginning is important if you want to make these kind of comparisons. Okay, so the type of transverse momentum dependent factorization that I'm talking about here is rooted, it goes back to basically the Collins-Soper-Sterman CSS formalism from the mid to early 80s, which is basically a TMD factorization and evolution formalism. There have been refinements and updates to it since then, but the basic idea is there. So all of this sort of theoretical technology exists. And so another way to ask what I'm doing is to say, why am I worried about formulating things in a different way if we've already got something totally reliable and understood that everybody agrees on? And one way to answer that would be for me to write down what that looks like. If I take, say, a typical way that a cross-section, like the Drell-Yan cross-section, gets expressed in the Collins-Soper-Sterman formalism, in the CSS formalism, it might look something like this. And if you're sort of, your eyes are glazing over and you don't like looking at this complicated formula, then you're getting exactly the point that I'm trying to communicate here, which is that it's a complicated formula and it's not at all obvious where the intrinsic or the non-perturbative, the main types of non-perturbative effects reside inside of this formula. So you see a lot of things. You've got everything in transverse coordinate space. So there's a Fourier transform here, and you've got you can see some collinear PDFs, okay, with a scale that depends on transverse coordinate in a somewhat complicated way. You've got some things here that you turn out to be perturbatively calculable. You've got some exponentials involving logarithms that also turn out to be perturbatively calculable. And I haven't written out what these objects are, but they're all things that have long expressions in terms of alpha s. Then you've got these G functions on the last line. Actually, those are where the non-perturbative effects essentially reside, but they've been sort of sequestered away from the rest of the formula. But how do you take, say, some particular theory or model or description of non-perturbative physics that you might want to test and embed it in a formula like this? So for example, some like a lattice calculation of transverse momentum dependence. How do you put that in here? Somehow it should be with the G's, but if you look at that and you're not really sure how to do that, then you're getting the idea behind what I'm trying to do here. Okay, so that's all of my introductory statements right there. What I mean by a hadron structure-oriented approach is to adhere strictly to the TMD factorization logic throughout. From the very beginning, we just want to isolate the TMD PDFs identified with their operator definitions and be able to study them as directly as possible. You'll see what I mean here once I start talking about it. In the process of that, we'd like to be able to interpret what we're doing in terms of structure. So in other words, stay as close as possible to a parton model interpretation. Now, you can't maintain really a literal parton model interpretation, but you can get very close. We want to preserve the relationship between different types of correlation functions, again, and as much as possible, as much as allowed within QCD. So in other words, we integrate over transverse momentum. We get infinity, but if we say regulate the integral over transverse momentum, we'd like to be able to relate that to the collinear PDFs in as direct a way as possible. So maybe integrating up to some cutoff. And we want to make it so that we can, without much trouble at all, just inject whatever particular description of non-perturbative transverse momentum dependence we'd like into the full TMD factorization formalism and be able to then use it to make predictions at all different scales, use the evolution to go to all different scales and test or study these different types of non-perturbative approaches. So if your favorite approach is, say, the bag model or something, and you want to put that in the TMD factorization and evolution, you should be able to just slot it in to a hadron structure-oriented approach. Okay, so now that's really the end of my introductory statements. And I want to now describe in more detail what this is all about. So the first thing I need to do is really review the way TMD factorization is typically set up, the more conventional way that is. There's a lot that goes into that. It's kind of technical, but I hope I can give a sort of bird's eye view that draws your attention to the most important landmarks in the steps that are normally followed. So first of all, if we're working with a TMD PDF, say F for some quark, for example, a quark in a proton, when we talk about the evolution, we generally like to switch to coordinate transverse space. So the coordinate transverse coordinate is BT, conjugate to KT, transverse momentum. And the evolution equations that the TMD PDFs satisfy are actually quite simple. I've written them down here. There are 3 of them now. And they're just simple first order linear differential equations that are almost trivial to solve. Let's look through the main features. So we've got actually now 2 auxiliary scale parameters. So in, say, DGLAP evolution and standard evolution, you just have some mu, but the Wilson line or the light cone divergences ultimately end up with an extra parameter we call zeta here. And so we need an extra equation for that. The equation that governs the zeta dependence relates the derivative with a object we call K, the Collins-Soper kernel. So this is the CS kernel. And it depends only on a transverse coordinate and on the renormalization scale mu. And I've had it blue here because in principle it can be non-perturbative, but large sizes or in momentum space at small transverse momentum, it can be non-perturbative. It generally will be non-perturbative. It's related to soft gluons. Everywhere I have put blue is indicating an object that can be non-perturbative. Okay, the other equations are for the renormalization group scale dependence of the TMD PDF, again in BT space, and there is a perturbatively calculable anomalous dimension gamma. And there's a renormalization group equation for the CS kernel itself, again with a perturbatively calculable anomalous dimension, gamma k. And these allow us to relate the TMD PDF at any pair of scales mu and zeta to any other pair of scales. Typically, we want to evolve them to a scale that is related to the overall hard scale so that we can optimize perturbation theory calculations. So yeah, that's the first step then, is to start at some scale that is small enough. Really, what we want to do is start at some input scale, so some small scale, but one that's still large enough that we think that it's at least reasonable to try to use factorization theorems, and then evolve these equations to relate the PDFs at the input scale, and then use these evolution equations, solve them exactly, which is straightforward to do, to relate them, to relate the PDFs at some input scale Q0 to PDFs at any other scale Q. Okay, so that's one step, but it doesn't take full use of what we can use QCD factorization and perturbation theory for. It doesn't make full use of our knowledge of perturbation theory and factorization because these PDFs have this BT dependence. Now, if we say start, for example, at some input scale Q0, and this would be Q0 squared zeta. Okay, as long as BT is something like 1 over Q0. Okay, Q0 is large, so alpha S evaluated at Q0 would be a small perturbative expansion parameter. And we could evaluate this PDF, just calculate the operator definition using collinear factorization by expanding this object in an operator product expansion. We could do it at fixed order. There's only one hard scale, basically Q0, and we could use that to describe the contribution from BT around 1 over Q0. Now, the trouble is that if BT becomes much less than 1 over Q0, then we essentially have two hard scales, Q0 and 1 over BT. They become two separate, different hard scales. And perturbation theory isn't set up to deal with that. So we have to do another step in the evolution. So in other words, we have this addition to the main evolution equations, which says that if we take one of these PDFs, we can expand it at small BT, okay, in another collinear factorization. So collinear factorization meaning we can write it as a convolution of something hard, this is C, then it just involves BT and the various scales, convoluted with an ordinary collinear PDF. And we can do that with the errors being suppressed by powers. I'm not saying exactly what power here, but generally be BT squared, but some powers of BT times, well, lambda QCD or some small non-perturbative mass. So if BT becomes very small relative to these mass scales, or 1 over those mass scales, then we can drop these contributions and use this to calculate the TMD PDF. So we'd like to actually combine all of these together. So, and the Collins-Soper kernel also has a perturbative expression at small BT. So again, if BT becomes much less than 1 over Q0, then we have to somehow switch from a scale Q0 to 1 over BT if we want to extend the discussion to very small BT. Now, none of this really has any practical immediate impact if we're looking only at processes, like physical processes like Sydney inclusive DIS at Q around Q0, because we don't really have access in those processes to the BT much less than 1 over Q0 type of physics. We don't have that when you have Q around Q0. So if you're not setting things up explicitly to deal with that, then you would miss that. Okay. And by the way, when we talk about this small BT behavior, if we're talking in transverse momentum space, that would simply be describing that tail at large transverse momentum. And the analog of that would be to say that at large transverse momentum, the TMD PDF is like 1 over KT squared times something that you can expand in collinear PDFs in a hard factor, where the hard factor only depends on logarithms of KT. Okay. And the problem is that if you have logarithm of KT over mu, and KT is much larger than what you have set mu to be, then these logarithms start to explode and you start thinking about wanting to do some kind of logarithmic resummation or something. Okay, so how do we normally deal with that? Well, we say at small bt, we want to take into account that at large bt, you've got all the non-perturbative physics in there and we want to keep it. But in the limit that bt is very small, we want to switch to using this 1 over bt scale as the hard part. So this requires that we at least define what we mean, at least to an approximation, by large transverse sizes and small transverse sizes. And we don't want to set things up so that things are very sensitive to that demarcation. The way this is normally done is specifically trying to avoid having that kind of strong sensitivity. The challenge here is that there is no specific point in BT where we understand things to just switch completely to be non-perturbative, and there's no point below there's no point in BT where we can say we just go below that and everything is perturbative and we just calculate as many orders as we can. Okay, there's a fuzziness to this question of what is large BT and what is the small BT, but we can arbitrarily demarcate two different regions where we start to feel comfortable using perturbative treatments in one and where we start to worry about non-perturbative contributions in the other. So we'll call that point B max. Okay, traditionally it's B max because it's the B above which you want to stop relying entirely on perturbation theory. Okay, so if you want to be very conservative, you would use a very small B max and say that only the very smallest transverse size region would you use this equation. Okay, we're essentially trying to make this error term as small as we can. But you might be brave and try to push B max larger so that you can describe as much of the BT as you can. Okay, but the formalism should be totally independent of how you demarcate these two regions. Okay, that's an important point. And in practice, we implement this with what we call a B star mechanism. I'm sure many people have heard of that. So the idea is simply to say that we're going to define a new parameter or a new coordinate, basically just a coordinate change. We say B star is a function of BT, and actually it could be any function that we want. It's totally arbitrary, as long as it has the properties that for very small BT, it basically goes like 1 over BT. So this is for BT much less than B max. And for very large BT, it goes to B max. And then we hope that it does it relatively smoothly so that it makes our calculations nice. Okay, now remember, at the end of the day, we should be able to put everything together and not have any dependence on B max or B star. Or if we're making approximations, we should be able to say that as we improve our approximations, we get rid of this B max dependence or B star dependence. Okay. Okay, now once we've defined B star, we can also actually define a mu B star, which is basically up to an overall constant 1 over B star. And then we can say that if B is very small, the scale mu B star becomes like 1 over BT. And if B is very large, if BT is very large, it goes like 1 over B max. And so it's a scale that is always large in the sense that it's always at least as large as 1 over B max. Okay, and we can use that as our scale. So the steps are, we first evolve so that we relate an input scale Q0 to some final scale Q. Then we evolve that input scale Q0 to this other scale, mu b star, to allow us to make use of this equation and drop these error terms. Okay, so what we're trying to do here is maximize the amount of input that is coming from purely perturbative type calculations. Okay, but we still want to not give up on keeping the non-perturbative parts. So how do we deal with that? Well, what we do is we say we define a new function, but the way we do it is we say take the TMD PDF, the exact TMD PDF, this is intended to be the exact object as defined by the operators and so forth, and write it as the same object, but simply evaluated at a different B. So instead of evaluating it at the normal BT, evaluated at B star of BT, and then we haven't changed anything. If we just multiply that by the ratio of the function evaluated at the normal BT divided by the ratio, but divided by the TMD PDF at B star. Okay, so what we've done here is we've said all of the non-perturbative physics now, the effects of the non-perturbative physics are localized in this factor right here. Okay. The nice thing about this is that actually the mu dependence cancels in the numerator and denominator. So this non-perturbative factor here is renormalization scale independent. And conventionally, we take the logarithm of that and call that negative, this g function. And this is one of these g functions that we saw in the CSS formalism. This is basically like that. Now you have to do a similar thing for the CSS kernel. Okay. It also becomes non-perturbative at large BT. So the way we define a g function for that is we say it's the g function for the CSS kernel, the CS kernel, is the difference between k evaluated at B star and BT. And so that also ends up being inside of an exponent. Okay, so the steps now are evolve from an input Q0 to Q. Now you have an expression for the TMD PDF in terms of the TMD PDFs at Q0, and then some evolution factors. Then you evolve those TMD PDFs at Q0, again from Q0 to mu B star, and you produce some more evolution factors. And then you do this manipulation, and you've got all the non-perturbative stuff separated into separate factors. And you've got the TMD PDF itself only evaluated at BT less than Bmax and with scales mu B star. So you can justify this expansion, drop the small BT error contributions. Then what's usually done is that, well, the G functions are more or less guessed at. You propose an ansatz. Often it's something proportional to BT squared. So GK, for example, is often just a constant times BT squared, or maybe something linear, depends on the treatment. And that gives you the final CSS formalism. So let me just summarize again. We start out with the most general solution to the TMD evolution equations here, where I have the TMD PDF and the TMD fragmentation function. They're both evaluated at some general mu. And then I end up with some evolution factors associated with evolving from Q to Q0, and then from Q0 to mu B star. And I end up with an exponential of these factors that I defined over here. Now they're containing all the non-perturbative physics. And I have these functions, these TMD PDFs. These are the TMD PDFs at the scales mu B star and with B star as the arguments. And so what I can do is I can say, let's take this small bt operator product expansion or collinear factorization expansion, drop this term, okay, and put a and put a superscript OPE for operator product expansion to indicate that we made an approximation there. And we'll have errors that are coming from basically the Bmax, because these functions are never evaluated at anything larger than Bmax. And if Bmax is small enough, we can just then neglect these. Okay, and this is essentially what reproduces the standard form that you often see the solution of the CSS equations. So way back here at the beginning, when I wrote this, you see all these G functions sitting there. Okay, it's a little bit different from this, but the basic idea is the same. Now, there are some very nice things about this. The main one is that notice that now all these parts that are calculated perturbatively up here, and K and these, they're all blue, but they're in the small BT region, so we can express them all in terms of collinear factorization. All of those are totally independent of any non-perturbative parameters. Now they depend on Bmax, okay, but remember that Bmax is by construction something that doesn't have any effect on the final result. So if we change Bmax, we get no change to anything. So Bmax is not a parameter. Okay, so we can say, at least if we're taking this equation and using it in the way it's strictly set up, that these parts are totally independent of anything non-perturbative. Okay, now there is non-perturbative stuff here. Essentially what's happening is that as you vary Bmax, you're shifting contributions between here and these G functions. So that means the G functions in principle should contain stuff that you can identify as perturbative. Okay, but it also contains non-perturbative stuff. And when you vary Bmax, you're just moving stuff around between these two lines, sort of like a renormalization scheme transformation. Okay, so I've followed all the definitions literally, and I haven't done anything that I think is obviously wrong, but this does cause problems, and we'll need to see how that happens. So why would that cause problem? Okay, well, there are various ways that you can test the consistency of this approach. So one is, well, first of all, recall that the starting point is expressed in terms of these TMD functions, the TMD PDF and the TMD fragmentation function, that have completely well-defined definitions in terms of quantum field theory operators. Okay, so there's no ambiguity about what those should be. And also, if we look at each one by itself and consider its behavior when, say, K1T is around Q, okay, then there's an object with only one hard scale. We can look at the situation where Q is very large. Then really we have to be able to expand it in a collinear factorization expression that looks something like this. Okay, or for an individual TMD PDF, something like this, namely 1 over KT squared times a bunch of stuff that just involves collinear PDFs. Okay, so essentially we've got two different ways of calculating the large transverse momentum, the transverse momentum of order, the hard scale. And both of those two different ways of calculating should be are completely well justified. Okay, this way is well justified. The other way is to take what we got by doing all the evolution steps that led from here to here and here, do all the evolution in B space, and then express everything in terms of evolution factors, then transform back into KT space. That's also a valid way to do things. And we should get something that's more or less up to errors associated with truncating perturbation theory and so forth, we should get something that's very similar. Okay. And also, we should be able to verify that if we've done everything correctly, or reasonably at least, then we should get this independence on Bmax that I just discussed here. Okay, we should be able to say that if I vary Bmax, there isn't, and if I vary the G factors in accordance with the variation of Bmax, I shouldn't get a huge change in the PDF or the cross-section, depending on what I'm calculating. A nice thing is that you can check all these things in much simpler quantum field theories than in QCD. So an example I have is a paper here in Physical Review D that just looked at a scalar Yukawa theory. It's basics of factorization, where we basically go through these various steps, but for a situation where we don't have to worry about non-perturbative physics, real large coupling constants, and where we don't have to worry about all the complications with gauge invariance and Wilson lines and so forth. And you can see all the things we expect appearing. So what we have here is the F1 structure function in DIS, I guess in semi-inclusive DIS here. And the W term, this is the part of the F1 that comes from TMD PDFs. So it's what we're talking about here. And asymptotic is the transverse momentum of order Q approximation to that. And you can see that as transverse momentum goes up, the two just telescope right in on top of each other. Bmax dependence should vanish as Bmax gets small relative to 1 over the input scale. And here is what we get for a TMD PDF versus, and this is in coordinate space, for different values of Bmax. And once the Bmax gets below about 1.5 inverse GeV, it just goes on to the exact unapproximated, unfactorized, unapproximated TMD PDF. And for Bmax below that, there's no change. Okay. So it's easy to check these things in these sort of toy examples. In QCD, in actual applications, it tends to be quite a bit worse. So if we try to do, for example, this kind of, or we want to look at, say, F1, a cross-section, if we want to look at this kind of observable, but now in real QCD, here are some examples, and you can already see that they don't look quite so nice. For now, just ignore what this FO means. It's not really relevant for this discussion. Here we have a process. This is E plus E minus into back-to-back hadron. So it's one that only involves TMD fragmentation functions, but all the comments that I've made apply just as well to that process. And you see the calculation as it's done with TMD fragmentation functions here in blue at Q equal to 12 GeV, and then evolved up to 50 GeV, blue here. And here's the ratio of transverse momentum to the kinematical maximum. And in green, you see the large transverse momentum approximation. And especially for the lower Q, there's not even a rough approximate agreement anywhere, regardless of how large in transverse momentum you go. Okay, down here is an example for semi-inclusive DIS. Here's the paper, the study that was done back in 2015, pointing out the issues that arise. So for one thing, well, let's look at just the baby blue is just the W term, and then NLL is the way the evolution is being done. And the green, again, is the large transverse momentum approximation. And this is for Q squared of 10 GeV squared. And even when the transverse momentum are more or less exactly the same, there's there's not even qualitative rough agreement between those two curves. So something's going funny here. You might ask, what does transverse momentum of order the hard scale actually mean? Well, I mean, one thing that should definitely be true is that the non-perturbative parameters that we have in the TMD PDF shouldn't affect the behavior around transverse momentum of order Q. So in our parameterization, that's one way we can test that things are consistent. Make sure that when we vary the non-perturbative parameters, they're having at most a negligible effect at QT of order Q. And if they are, then probably at QT of order Q. Is there a region where transverse momentum is large relative to the non-perturbative scales, but still small enough that you can expand, small enough relative to Q that you can expand in powers of QT over Q? So this is a question here. And of course, that has to be the case if we, for example, fix this ratio, let's say QT over Q is fixed to some numerical value, and then we take Q to infinity, then you eventually reach this point. Okay, and there we definitely should have agreement between calculations in collinear factorization of the W term at large transverse momentum, like QT over order Q, and the TMD calculation done directly. How can we look at a graph, for example, and maybe estimate where that large value of QT over Q is? Well, one way to do it is to remember that when we do TMD factorization, I mean, normally we do the evolution in BT space. So what are we doing when we do the evolution in BT space in this kind of region, this middle region of QT? We're effectively doing what is equivalent to resumming large logs of BT times Q. It's actually analogous or equivalent to resumming logarithms like this in momentum space, or if we're talking about the cross section, maybe I should use QT rather than KT. As QT gets small, now as QT gets much larger than Q, the logarithms flip sign. If QT is of order Q, they're basically negligible. If they get larger than Q, they flip sign, and that's why you see this is the absolute value of the cross section. That's why you see a node in the graph here. This is where at the large QT approximation is flipping sign. Since it's going negative, that's obviously outside the physical region, but it's what comes out of these operator definitions. So a sign that you've gotten to large QT of order Q, is when you've gotten to that node right there. So certainly you should get agreement between the fixed order and the TMD ways of calculating before you get to that node. Okay. All right, but at the end of the day, the main point is that when you implement this using the usual steps, following the standard conventional steps that I summarized over here, this doesn't work out very well at all. Compare these graphs, where you should be comparing the green and the baby blue here, and the green and the purple here. Compare that with what we saw in the toy model case here, and you see that it's just not working very well at all. Right? We did our own calculation in QCD, not doing a fit, but just repeating the steps of the standard approach, the standard way of doing TMD phenomenology, just to see what's going on, try to get a handle on what's going on. And we can make the same point that I just made. So here is a calculation of the semi-inclusive DIS cross-section. Okay, again, ignore the fixed order part. So we're going to ignore, for the purpose of this presentation, the black dot dash curved here, and just look at TMD and ASI. ASI stands for asymptotic, so it's the large transverse momentum approximation to cross section. And what we're doing is we're saying, let's take For the G functions, typical form, okay, similar for the GK function. We also took something very typical from standard implementations. And we've got some non-perturbative mass parameters here. These should be small mass parameters. So it's often that these functions are, say, quadratic and BT squared. There's some more complicated ones out there, but they're all basically some kind of combination of simple functions with sometimes many parameters. Okay, and just choose some values for the masses that are, again, sort of typical. You see what we chose here, something typical for a non-perturbative mass. And then that gives the red curves here. So these are calculations done of the W term using the TMD PDFs. And then the blue curves are calculated in collinear factorization. Those are supposed to be the large transverse momentum approximations. And this is all for an input scale Q0. On one side, I've got a linear scale and just a short range in QT to blow up the region at small transverse momentum. You can see there's no agreement there and no converging of the lines at large transverse momentum. Of course, we expect not to have agreement at small transverse momentum, but it starts to become unsettling that they don't even really match out here very well. Once you get to QT over Q of order, something of order 1. And then over here, I go all the way out to 4 GeV on the horizontal axis. The vertical axis is now logarithmic so that we can blow up the tail type behavior out here. And you see that there's never really any region at large transverse momentum where the two start to match together. Okay, so that's just driving home the same point that I made with these graphs, essentially. We can use these graphs to sort of probe and ask the question of what's going on. The other thing is that if we vary these mass parameters in the non-perturbative part, the effect actually it's actually a really large effect for one thing, and it propagates out to quite large transverse momentum. The effect of varying m between a range of roughly non-perturbative scales produces a thick band in the red here. So that's putting some tension on this criterion. The other consistency test not listed on this slide, but back here, is again that we should have essentially no Bmax dependence. Remember, Bmax is not a non-perturbative parameter. It's this arbitrary sort of parameter for just deciding what we want to call large B and what we want to call small b. But if our approximations are reasonable, then any variation in Bmax should be a negligible effect on the cross-section. If there's a huge effect, it means, and especially if there's a huge effect at large transverse momentum, it means that our way of modeling the non-perturbative region has propagated into the perturbative part, which is what we essentially wanted to avoid by setting things up in this way to begin with. So that's also a sign that things aren't working out as well as we might hope. And this second plot here makes that point very clearly. Here we've varied Bmax. We take some fairly small values of Bmax where we should, in principle, be telescoping in on the true description. Like if we make Bmax very small, should be okay. And then up to values that are large but typical for what is used, and you see these huge bands, especially in the large transverse momentum tails. Okay, so this is just showing that if you follow the normal steps for implementing these equations, okay, things start to go wrong. So next step is to diagnose what's going on here, and that will tell us immediately how to try to fix it. So again, this kind of exercise allows us to diagnose what's happening, what's going wrong. And well, here, let me keep the basic TMD factorization formula up here at the top so I can gesture at it. The problems basically come down to the treatment of these G functions. It's this step where we go through back here and replace the large transverse size contribution in the BT space formalism with these exponentials of these quote unquote non-perturbative G functions, and then apply this OPE formula and drop the errors and drop these BT suppressed errors or these Bmax suppressed errors. That's really what the problems come down to if you drill down and try to understand what's happening. So in practice, what happens is that we replace the large BT with these G functions, and then generally you just introduce some kind of onsets, some kind of parameterization on the grounds that you're trying to parameterize non-perturbative physics. Okay, but there are several consequences to that. Okay, so again, let me just remark, it's these G function onsets expressions. First of all, the most basic issue is that you're essentially forced to decide on a value of transverse size above which everything is non-perturbative and below which everything is completely perturbative in the sense that you can use small coupling techniques. Of course, in real physics, we don't expect there to be this sharp, well-understood transition, but some kind of smooth transition where things are on one side start to become more dominated by perturbative physics and on the other side, more non-perturbative. And you end up in a sort of complicated trade-off. You want to choose a Bmax to be very small if you want to justify as much as possible neglecting these error terms. But if you choose Bmax to be very small, that means that most of the description of the cross-section is going to come from these G terms, which means that they're going to include these supposedly non-perturbative functions are going to include a whole bunch of stuff that should be described perturbatively using small coupling. So most of the work is going to be basically fitting stuff that's actually perturbative. On the other hand, if you want to maximize the amount of the cross-section that gets calculated using collinear perturbation theory, then you want to push Bmax to be as large as possible, but then you start to lose control over these errors that you drop. And essentially what happens is that Bmax starts to become like an infrared cutoff, and you now have infrared cutoff sensitivity inside the perturbative parts. If you make Bmax very small and use just some random onsets for these G's, then of course that's going to mess things up because you're using something like a quadratic formula to describe perturbative BT dependence. So I'm just trying to outline the problems that I hope are not that hard to see just on the surface. There are more subtle things going on here. For some of the more subtle issues, it's helpful to remind ourselves why we went through all these steps to begin with, sort of historically, what motivated this set of steps here, this arrangement. And the reason is that the applications are typically at very large energies, very high energies. It's large Q. So Q very large. So say something like electroweak boson mass. So something like that. And then the issue is what happens when you try to calculate things in collinear perturbation theory at values of transverse momentum that are small relative to Q. So we're starting at a very large scale. Okay, and then you go through a whole bunch of work to try to maximize the amount of the calculation, the portion of the calculation that can be done using as input only, just standard collinear PDFs and so forth, without any non-perturbative transverse momentum. And the way of writing this formula is designed to sort of maximize that. So the idea is to kind of quarantine all of the non-perturbative large BT stuff into these G functions. And at large Q and high energy applications, you maybe hope that they don't actually have a huge effect on the cross-section at the end of the day, so that you preserve as much predictive power as possible from the collinear parts. Okay, so that means that a lot of this work of, transforming from an input scale of Q0 to say a 1/BT type of scaling, all of that is designed basically to optimize for the region where transverse momentum is small relative to Q, but still way larger relative to some non-perturbative scales, like let's just say lambda QCD. Okay, where this is basically the dominant region that you're interested in trying to describe. Okay, and then if you have to put in these G functions to get everything right, that's fine. You want to say that if I change B max, maybe by a little bit, I just have to adjust the G functions a little bit to preserve the cross-section, and everything should be fine again. The problem is that if you then evolve downwards to say a smaller scale, like what's typical in many semi-inclusive DIS measurements, where you run as actually get access to the non-perturbative parts. So these non-perturbative parts are not in hadron structure oriented applications the extra stuff that you hope is not having a big effect, but they're actually the main thing you want to study. Okay. Now what happens is that you're at a value of Q that's usually just high enough that you feel comfortable applying perturbation theory at all, partonic physics. And there is no region then where transverse momenta is much smaller than Q, but also large relative to non-perturbative scales. You either have transverse momentum that is basically comparable to Q, the hard scale, or is in the non-perturbative region at very small scales. Okay, but that means that all of these manipulations that lead to this complicated formula, okay, these are actually trying to optimize to basically, in some sense, resum lots of logarithms of this form. But if transverse momentum is of order Q, that actually doesn't help at all. And in fact, it makes things worse if you're right close to the boundary where things are perturbative or non-perturbative. Rather, you want to say that when transverse momentum is of order the hard scale, you should just be able to use collinear perturbation theory, at least to some approximation. And that should be what you impose in the large transverse momentum region. All this other stuff is actually introducing a bunch of uncontrollable errors. So this is the point that I'm trying to make with these two statements here. A related issue is that, well, if you take the extractions of those non-perturbative G functions at very large Q, okay, that's where you're the least sensitive to the non-perturbative behavior, right? So you're optimizing this kind of resummation of many logarithms in a certain way of looking at it. And then you're where you're also not very sensitive to the truly non-perturbative type of effects, and where you have very small coupling. And then you take, in this formula, the way it's usually applied, you take Q and evolve downwards. And as you evolve downwards, coupling constants in various parts tend to get larger, and the contribution to the non-perturbative input, the non-perturbative behavior starts to grow. And so any errors in the non-perturbative description at large Q start to get magnified. This is essentially a kind of backward evolution problem, right? So ideally, what you would do is you'd optimize the description of the non-perturbative type of input at the smaller scales, and then evolve upward to make predictions rather than vice versa. And formulating things with these G functions in this way is really, in some sense, codifying this problem into the formalism. It makes it hard to see what's going on in some sense. Okay, and there's another consistency check that I haven't mentioned very much so far, but which also tends to fail pretty badly in the normal way of doing things with G functions and so on. And it's also very much related to this parton model interpretation and the desire to preserve it as much as possible, to be able to interpret things in terms of a partonic structure. And that is this relationship, the naive relationship that connects TMD PDFs with collinear PDFs. Okay, I've got an approximation here because we know that due to these UV divergences, it can't be an exact relationship. But it tends to be very badly violated in the standard sort of G function B star way of organizing this. Okay, and that is maybe a little bit surprising, because if you look at the way things have been set up, it looks like it should be preserved, at least reasonably, in that first blush. Because, well, for one thing, the way these g functions are defined is that they vanish at small bt like a power of bt. So basically, proportional to some power of bt as bt goes to 0. Okay, so those really, that is an indication that they're really only important at large bt, so non-perturbative, so on. And from that, you also can say, well, you can sort of derive, at least on the surface, you can sort of derive this relationship. Okay, how does that happen? Well, one way to think of getting this relationship, nice physically intuitive way to think about it, is to say that the TMD PDFs are really only describing the small transverse momentum where it's non-perturbative or it's related to structure and so forth. And so if we find some problem with divergences at large transverse momentum, maybe we should just correct this equation by putting some sort of upper limit, some k max. K max, typically something around q, you would hope. And then get this relationship to hold up to errors associated with basically alpha s at k max. Okay. Another way of getting that, though, is, well, an analogous way of getting that. You can, instead of putting a cutoff on kt, you could, in coordinate space, put a cutoff on small bt. So small transverse coordinates are where you go into the perturbative region. So you could say, do the same thing, and I won't write down the details, but the k max is, roughly speaking, conjugate to some 1 over b min. Okay, we had a b max. We could say if we cut off transverse coordinates below some b min, then we can preserve, hopefully, some approximation like this. Now, you can, however, remember that the g functions basically vanish like bt, and if you put in a b max, the small bt limit is proportional to bt over b max. Okay, but that means that the errors in this are going to be basically going like b min over b max, or some power of this ratio. However, remember what b max is. B max is something that we want to make as small as possible, so that we really quarantine as much as possible the perturbative collinear part of the calculation away from the non-perturbative part. So we have a motivation to make b max as small as possible. We also want to make b min as large as possible. You know, that would be like making this k max as large as possible to make sure that we get everything that should go into the TMD PDF to be in the TMD PDF. Actually, to preserve an equation like this, we'd want k max to be roughly of order the hard scale, and that means that b min should be roughly of order 1 over a hard scale. So near the input scale, b min should be like 1 over basically the input scale. And if the input scale is near the boundary between perturbative and non-perturbative, then b max should also be there. So this ratio is typically of order 1. This ratio is typically of order 1 when you're at, say, semi-inclusive, typical semi-inclusive DIS scales. So what that means is that this relationship won't hold to a reasonable approximation at these input scales unless you impose it directly on these g functions. So that means there are several things we should be imposing on the g functions if we want to get reasonable behavior. One is that the G function should transition smoothly into a perturbative description of the tail at the input scale or at slightly above the input scale. And it should preserve this relationship. And by that, I mean directly on the G functions. And the failure to impose those conditions is what leads to this kind of situation here. Okay, so all of this suggests how really to do things, how to proceed. It's not that difficult, it's just a change in the organization. Okay, so here on the right, I'm going to basically start to tell you what we mean by the hadron structure-oriented way of doing things. So it starts by basically embracing the TMD factorization view of this, adhering strictly to the logic. So we know the operators that represent these correlation functions, the TMD PDF and the TMD fragmentation function. And we know exactly how to evolve them using that set of 3 equations. They're very simple, and evolving from some input scale Q0 to some general scale Q is straightforward, and going from here to here using those evolution equations gives you something like this. And now the observation is that if we at the input scale could describe each of these functions for all BT, then evolving to larger Q would be a trivial matter. We just substitute them in here. Okay, so the idea is for the large BT, let's get these functions by using models and fits and all the usual things. And then for the small BT, use the requirement that we match onto the large transverse momentum behavior that's embedded inside the definitions to describe that behavior. Now, the only thing that makes things a bit complicated is that we're going to BT much less than 1 over Q0. Okay, then we have to do another step in the evolution. But at this stage, all of that is a scheme change. So if we've got a parameterization here, we just need to do one more renormalization scheme change to mu, basically going like 1 over BT at small BT, in order to be able to say that we've got a description of these functions for the whole range of BT. So for that, we're going to take these functions to be some parameterization at the input scale, and then to make sure that we can evolve to large Q and thus and still get the right treatment of the very small BT region, we're going to apply another application of the evolution equations to go from a Q0, the input scale Q0, to a Q0 bar. And Q0 bar is going to be some function, some smooth function, sort of analogous to what we did with mu B star, but some smooth function that at very small BT transitions from Q0 to 1 over BT. Okay, and applying this E will have essentially a negligible effect at the input scales, or at low scales where we're doing a lot of the hadron structure phenomenology, but will preserve the right behavior as you evolve to higher scales. The idea, again, is set up the parameterization for these functions, these input functions, to give the smooth transition to the right perturbative behavior at small BT or large KT if you prefer. And then just do one more scale transformation here. Notice, by the way, that this is an inverted way of thinking about the usual TMD type of resummation that you sometimes hear. So often the way things will be described at very large scales is that you start calculating high orders in perturbation theory, and you get logarithms like something like this. And then the question is, what happens when transverse momentum starts to get very small? Okay, relative to Q, these logarithms blow up. You have to do something with resummation or some kind of TMD, something. You have to do something to address the issue. The way it's well, and then eventually at some small enough QT, you would say, well, I can't resum anything anymore. I have to and start to worry about non-perturbative effects. the way I've described it here is the reverse of that. Instead, we're thinking at low scales, we start to have logarithms like this. Okay, but then these logarithms appear inside the input TMD functions. But then as you evolve to larger Q, you start to get access to larger and larger QT. And now that the logarithms, the quote unquote large logarithms you have to worry about are coming from transverse momentum getting large relative to this input hard scale rather than getting small. Okay, but the nice thing is that when transverse momentum gets large, you tend to get into a region where coupling constants are getting small. So we sort of address this issue with the backwards evolution. We invert the order that we're doing things here. Just putting in numbers these basic elements. So use the fact that we can talk about the definition of the TMD PDFs. If we understand their definitions, then in principle, they're uniquely defined at the input scale and for all transverse momentum, for all transverse coordinates and coordinate space. And then in constructing parameterizations to use for phenomenology, directly interpolate, transition between the non-perturbative description at small transverse momentum and a perturbative description at transverse momentum of order, whatever the scale is, and smoothly transition between those two regions. And then finally, impose directly on these parameterizations this kind of condition which appears in the parton model. Given that we know the definition of these TMD functions, we can actually calculate exactly what the relationship is between a collinear PDF defined by the integral up to a cutoff and say standard MS bar PDF. So we know how to calculate this quantity in principle and relate it to collinear PDF. So we can impose this kind of relationship directly on the TMD parameterizations. Okay, so this is essentially some of the main elements that go into this hadron structure oriented approach or reorganization or whatever you want to call it. So the steps are, first, make sure that all of this applies at an input scale at the lower scales where you want to maybe try to study the hadron structure, and then evolve up to larger scales. And then finally, we try to organize this in a way so that you can take any sort of model or parameterization or some description or non-perturbative theory and just inject it right into the treatment. Okay, you don't have to, it's highly non-obvious, I think, if you go back to the way it's usually written, to look at this equation, look at these G functions and say, well, I've got this non-perturbative approach that I like. How do I put it into this equation? And somehow it has to go into those G functions, but in the way it's written here, it's not at all clear how you'd go about doing that. So we try to set things up at least the best that we can, so that's possible. Okay, so those are the elements. There's way more in terms of details to talk about that I can't talk about in like an hour-long presentation. And so one of the reasons we wrote that first paper on my title slide is to provide a bullet point recipe sheet for basically taking any kind of modeling or non-perturbative or lattice or whatever description of the non-perturbative physics, and again, just follow a set of steps that allows you to inject it into the TMD evolution equations and use them and just sort of turn a crank to use them in a way that's consistent. Okay, the end result is that since we're directly dealing with the transition between the non-perturbative region and the perturbative region, the B star and the G function stuff just doesn't, you don't need to use it. Okay, we're not trying to quarantine the non-perturbative physics from the perturbative physics anymore. Since we're trying to describe the details, we're directly interpolating between the two. And by the way, instead of a hadron structure approach, we called it a bottom-up approach here. That's essentially evoking the forward versus backward evolution type of thing. When I've talked about this before, I've heard people contrasting it with standard CSS evolution, which I would say this is all standard CSS evolution. It's simply a different organization. It's not, the equations are the same, the physics is the same. Everything is the same. It's just how do you organize formulas so that you can optimally apply them to phenomenological applications where hadron structure is the main goal. Okay. And even though I just said that you don't need to use B star, B max, or G functions, you still can in this formulation. And it maybe if you want to just keep using existing setups, you can write things in terms of G functions. It's just that you don't need to. So if you need a set of steps to translate some treatment in this HOSO approach into G functions with a particular B max, just have a look at the section 9 of that first paper again. Okay, so now I thought I would give a few demonstrations of how things improve if you switch from that standard conventional organization of formulas into the HSO hadron structure formulation. So I said that we want to be able to take any sort of non-perturbative description of the small transverse momentum region and just inject it into the formula. So I'm going to try using two different ways of describing, two different models, if you like. One is a Gaussian model. So core means it's describing the very small transverse momentum region. So it's very common to use a Gaussian functional form to describe transverse momentum. We'll do that for both the PDF and for the fragmentation function. And you've got some mass parameters. Well, F is the PDF and D is the fragmentation function. And another model that's frequently invoked is a spectator type of model, which is essentially giving PDFs that go out, that fall off more like a power than an exponential. So we've got some model parameterizations here. Now, let me just remind you what we had before when we used a Gaussian-like description. A Gaussian-like description in the conventional approach is when the G functions are just quadratic in BT. So something proportional to BT squared. And we let these n parameters to be whatever we want, but we didn't impose any of these conditions like that when you integrate, you get back the collinear PDF, or that you get a smooth transition or anything like that. And we got these disagreements, and we also got an uncomfortably large amount of dependence on the non-perturbative scales, even in the perturbative region. Okay. So if we basically do the same exercise, but now using these Gaussian inputs, so essentially the same philosophy of trying to describe the small transverse momentum using a Gaussian, but now you see that the non-perturbative description telescopes in right on top of the asymptotic large transverse momentum description of the calculation of the TMD PDF or the TMD cross section. So on the right here, we again use that Gaussian type of description of the small transverse momentum. So it's in the same spirit as what we have on the left here, but now we're imposing all these conditions like that when you integrate over transverse momentum, you get back the collinear PDFs, and that you get a smooth transition to the large transverse momentum dependent behavior. And you can see that here with all these red curves indicating the non-perturbative, or actually the full TMD PDF in the hadron structure oriented approach, are going right on consistently to the perturbative calculation once QT gets to be sufficiently large. And also when we vary these non-perturbative scales, the effect doesn't propagate way out to large transverse momentum. Okay, and this is all by construction, of course, now. But now we can basically tinker with these scales. If we're doing a fit, for example, we can mess around these scales these scales that describe the non-perturbative small transverse momentum behavior. And as long as those scales aren't getting like wildly large, we can be confident that the effect isn't going to propagate into a region that they shouldn't impact. Okay, and just for fun, here's the same thing on the right, but now with this spectator model. And since the transverse momentum is falling off more softly, not like a Gaussian, but like a power, the effect of the transverse momentum, the TMD non-perturbative scales, continues out to larger values of transverse momentum, but you see it still telescopes in right around that large transverse momentum calculation. Okay, and finally, I just thought it would be nice to show the individual TMD functions in one situation. So the Quark PDF in this calculation, these are not fits, by the way, these are just illustrating the procedure. So this is what an up-quark TMD PDF looks like. You see that we're able to, on this logarithmic scale, these are big variations, so we're able to adjust the behavior at small transverse momentum at will. Once the transverse momentum gets above about a GeV or so, it telescopes in onto the perturbative tail, and same for the fragmentation function, the TMD fragmentation function. Okay, so I thought I would end by comparing with some actual phenomenological extractions, see what's going on. So these are some Pion TMD PDFs extracted from the JAM collaboration, and here's the link to the paper here. And I've got the PDFs here at 2 different values of X and at a range of scales. And I've also marked with dotted lines the points where the transverse momentum over Q is 1/4, 1/2, and 1. So this is when KT is equal to Q. So in the literature, people will typically say that transverse momentum is large once it's about, say, 1/4 of the hard scale Q. So maybe 0.25 or 0.3. So somewhere in this region. And so I'm highlighting that region in each of these cases to show that, especially at the lower values of Q, you really don't have even a rough qualitative matching between the TMD curves, that's the solid curves, and the large transverse momentum perturbative calculations. Okay, so that's why, if we go back to my introductory slides, and I showed, this is from the same paper, this conclusion that the shapes of the non-perturbative parts of the pion and proton are different. That's this conclusion here. That's why I put question marks around there. Okay, so this is the same slide that I showed at the beginning. Just another example of a existing phenomenological treatment is this set of fits using the MAP TMD PDFs, and here's the link to the reference here. And again, I've put with dotted lines the halfway marks and the 1/4 marks. And again, you see not really even any qualitative agreement, especially at the lower values of the hard scale. Okay, so my proposal is to improve things on this front using this hadron structure oriented way of organizing the G functions, or actually not even using the G functions, but of organizing the non-perturbative input. So to summarize everything, I think what I hope to have shown in the last few slides is that this hadron structure way of doing things improves consistency overall, okay, between the description of the non-perturbative, what we'd like to identify as the structure or non-perturbative or intrinsic or whatever you want to call it when you're talking about understanding the non-perturbative behavior, and separating that out from the perturbative behavior. So it's especially necessary in cases where we care about, let's say, what the shape of a tail looks like. So if we're studying, say, the C-quark distributions and trying to compare them with valence quark distributions, we're often talking about what does the tail shape look like. And for that, transitioning between small transverse momentum and large transverse momentum, and getting a handle on doing that is, of course, going to be important. Okay, and I think it's especially the case that something like this has to be done if we want to keep a handle on, we don't want there to be just a total proliferation of parameters and different ways of doing things, different resumming things this way, resumming things that way. We want to make a system that is predictive and falsifiable. Finally, I would say, again, this isn't a totally new formalism at all. It's just a reorganization of standard formalism. It's the CSS formalism, just with the non-perturbative part as the focus of attention. I think I'll stop here then. Please send me email or leave me comments or whatever if there's any questions or if you'd like to have a discussion separately. There's a lot here that, of course, I can't talk about in just an hour-long presentation. So continue the discussion in another context. Okay, thank you very much.